Okay.
I can see it now, yes.
All right, perfect.
Okay. Well, thanks for inviting us. So I'm Heather Bedle, and you've already introduced me and David. So we're up at the School of Geosciences. We both work in different ways with the AASPI consortium. That's up there, where one of our main focuses is on trying to get more out of the seismic data. And when we were approached to give a talk, David and I kind of came up with this idea, and we thought it would be fun to kind of bounce back and forth between each other for the talk and have two speakers. You get to hear two speakers' voices. So what we're going to be talking about is trying to understand what's going on within the machine learning with some tools, explainable AI tools. And the one that we're talking about today is the SHAP method, but we have a few others that we've been working with that will hopefully be showing an image or some new research soon. So if you'll hit next, David.
Sure.
The outline for my talk is pretty straightforward, or our talk. I'm going to cover some basic seismic attributes. I don't like to assume anybody already knows what I'm talking about when I get started. And then we'll talk a little bit about machine learning, why we want to use explainable AI. And then we're going to focus on two different case studies that we've done with SHAP, one with seismic and one with another type of data that I just thought was interesting to throw in there. So if you go to the next slide, David, I like to start super simple in case somebody isn't aware of what seismic reflection data is. So this is, an image from one of my course notes, where I like to remind folks that what we're doing is pretty much sending energy down into the subsurface, and where there is a acoustic impedance reflection or acoustic impedance difference between the rock layers, some of the energy is reflected back up. So next. So what that ends up creating for us is a 2D or 3D grid of lots of rock interfaces. And so this is our standard seismic amplitude kind of map. We've got the difference between the red and the blue horizons, showing us all the different rock layers. We can look at the frequency, we can look at the attribute. And I think I recognize about half the names on this list, so I know we're all expert interpreters. And so we can pick out different stratigraphic and different structural features in here. If you go to the next slide, David. As many of you know, this started back in the 1970s with seismic stratigraphy, is where we really were able to incorporate the well log data and the patterns we saw in the wells and relate them more to the patterns we saw in the seismic. And so that was back in the late 1977, I think, was the AAPG memoir. So good year, because I was born then. If you go into the next slide, David. And then as the technology improved, we were able to start collecting 3D data, processing 3D data. Nowadays we're getting more and more high resolution. And so we can look at data not only in the vertical section, but also in map section. And so that allows us to do what we call seismic geomorphology. And so this is a classic image from one of Henry Postmentier's papers a few years ago. And so that adds in that third dimension. If you go to the next slide. And so what we do as seismic interpreters is we're looking for patterns, patterns that we could relate to our kind of geologic interpreter knowledge. So we're looking for those patterns in the seismic data, whether it's in the vertical section or the map view or an arbitrary line. We want to see geology in the seismic data. And if you go on to the next slide. But of course, there's ways we can see more than just the seismic amplitude data. And one of those ways is applying seismic attributes. And so I always like to say to everybody, like seismic attributes, well, it looks magical. To some of us, it's just math. So it's just focusing on different parts of the waveform, the patterns of the waveforms that are next to each other, to help us visualize and see those geologic patterns in the data. If you'll just tab a few times, David. I think this was the one slide I animated. And so pretty much stop there. Okay. No, yes. Let me see that seismic. So pretty much a good geologic attribute, it's either sensitive to the geologic feature, it's sensitive to some property of the reservoir that we're interested in, whether it's lithology or the fluid content, and it can help us see the structural and depositional environment a little more clearly. And so there's There's way more than 50 attributes. I don't know why I keep 50 attributes on this slide. One day I'm going to have to see if I could calculate or research how many different attributes there are, but there's many of them that we use. And a lot of times when we're doing an interpretation, we're using multiple attributes at once. And so if you just tab once, David. And so this is an image from Kurt Marfort's and Satinder Chopra's textbook, where they show this picture from the Gulf of Mexico shelf, and we're looking at an amplitude image, map view, and we could see some patterns, some light and dark in the amplitude. But we could spend a bit of time staring at this, and I think a lot of us could tell there's maybe some faults, maybe some channels in there. The amplitudes are probably some different lithologies. We know it's Gulf of Mexico, clastic. But if we just spend 2 minutes and hit next, we can run a coherence attribute and see the edges, the differences between the waveforms that are next to each other. And so really quickly, we can use this attribute to improve our confidence in our interpretation and realize that there's a lot of cross-cutting channels in the area of different sizes and different sinuosities. So if you go to the next slide. So I'm just going to highlight a few, and then I'm going to hand it over to David. So one of, I think, the most, well, okay, it's not the most classic, but it's my favorite attribute, is coherence. And so coherence is where we're comparing one waveform to the one right next to it. So kind of doing a trace by trace or a trace by several neighboring traces in a cube. And it's really great for mapping discontinuities and chaotic areas. And so here we're looking at some data. This is Gulf of Mexico, a vertical section. And what we can see is the areas that are blacker in color are less coherent. Areas that are whiter in color are more similar to the waveforms next to them. So we could kind of pick out some draping sediments that I've pointed an arrow to in the middle and on the right. And we also see very chaotic in those darker colors, something going on. All right, next. So we can add to that, we can run another attribute. This is the total energy attribute that looks at the overall amplitudes, and it can help us discriminate, well, not discriminate, but get some ideas about lithologic variations in the fluid contact. And so we can see there's very little energy in those blue areas that were also very chaotic. And we've got more energy kind of oscillating from pink to green to pink to green, with a bright and dim reflectors in those draping sediments. All right, so next one, trying to build a picture here, a story. Another attribute that we could use is spectral bandwidth. And so this lets us see the range of frequencies that are in the seismic image that we're looking at. So we could look at the overall frequency bandwidth and try to get an idea of if the lithology and fluid variations are varying the bandwidth. So in the draping sediments, we can see some alternating bandwidths, probably some layering of different lithologies. And in that chaotic low energy zone, we've got a wider bandwidth. So perhaps there's a little bit less attenuation happening. Next slide. And then finally, we've got GLCM contrast. So this is a texture attribute that's used a lot in photography and imaging, but we've been applying it, I don't know, like a decade maybe or so, to seismic images also. And so the GLCM contrast kind of lets us image the contrast between the neighboring pixels. And so it characterizes heterogeneity and spatial variations. So we can see in the draping facies that we've got a low GLCM contrast. It's whiter, lighter in color, so perhaps more homogeneous, maybe the same lithology. And in those darker areas, we've got a higher GLCM contrast. So it's varying a bit more from pixel to pixel, which gives us some information too. So if you go on the next slide. So, we can run through a whole bunch of different attributes that give us a lot of different information. But as you noticed, I've been going through them one by one. So hit next. So of course, the question is can we visualize or can we detect patterns using more than 2 or 3 attributes and co-rendering them together at one time? Hit next. And of course, yes. So this is where we get to the point of the talk. We want to add in some machine learning. And so I'm going to pass it over to David.
Thank you, Heather. So we know we can apply machine learning, as Heather mentioned, to try to look for patterns with all these attributes and try to summarize all the information and somehow make a seismic interpretation. But then you can get a result like this. Like for example, in this paper, we're looking to differentiate between 3 areas: mass transfer deposits, salts, and conformal sediments. And you say, okay, this is a nice result, but how the seismic attributes are contributing to this result? How is this happening? So what we can see is like if we put a plot here from easy to understand to difficult to understand and lower performance to higher performance, we have linear regression is easy to understand, lower performance. We have decision tree algorithms, like a little bit more complicated, but still easy to understand and somehow good performance. Then we have random forests, tend to be really nice performance, a little bit more difficult to understand that decision tree and linear regressions. And finally, we have deep neural networks. They can be very deep. That are really high performance, but are difficult to understand. We usually have like a result, and then we have input, result, and that's it. So is there a way to understand like data to geology relationships? Try to understand, okay, these are my inputs, and then how the machine learning algorithm is using these inputs to make the prediction. So what we are using is the SHAP method, the Shapley additive explanation methods that was developed by Lumber and Lee early in 2017. So this method allows to quantitatively estimate model interpretability. So how it works, this is a general idea. Imagine that you have 3 phases, MTD, salt, and conformal sediments. We have the same number of samples per phase, so we have 33% of probability of having each, well, 33.3%. So we have 33%, and then we know that a certain voxel, a certain data point was classified as salt with a 91% probability in the prediction. So now what we do is we can understand how the attributes are being influencing the final results. So for example, we start for 33%, we see that, oh, this data point is characterized by low total energy, that increases the probability, then low coherence, that increases the probability, high reflector convergence, that increases the probability to maybe 98%, but then in this data point, we have low GLC entropy, and that's decreasing the probability. So at the end, with all these contributions, we have a final 91%. So using SHAP, we can understand how the machine, the algorithm, is using these inputs for the prediction. So this is a simplified workflow that we did in this research. We have a seismic volume. Then we perform a sensitivity analysis. We have our original seismic attributes. Then we apply a water filter to the seismic attributes to try to improve the signal to noise ratio and the quality of the attributes itself. And then we also have a case number 3 that is add noise. What happens if we add noise and actually decrease the quality of the attributes? Then with these 3 cases, we do some pre-processing that is just like scaling, select your training validation data, all those pre-processing steps, and train a random forest to differentiate between these 3 phases, NTD, salt, and conformal sediments. Then we apply SHAP. One of the good things about SHAP is like it allows you to have a global interpretability. We're going to show some results about that. And you also can have local interpretability. So in your phases prediction, you can go to a certain data point, and then you can explain how the attributes are used. So the data set is located in the Gulf of Mexico. This is just like the area we are using 5 lines for training and 1 line for validation. In the PowerPoint, we are going to show you line AA prime to show you the representative line for all the hyperparameter search and the model optimization. And then we have GG prime, that is just a vertical line that we use as a test line to assess the performance of the model. So we are going to show the results using AA prime and GG prime. So the 3 target seismic phases, as I mentioned before, as mass transport deposits, salt, and conformal sediments. So the salt tend to be characterized by low amplitude chaotic reflectors. The NTDs are more heterogeneous. Sometimes you have more high amplitude coherent reflectors, and then you have low amplitude chaotic reflectors. You have this combination of patterns. And then the conformal sediments, we have to clear the phases or seismic response. We have a really high amplitude parallel to subparallel reflectors in the middle of the mini basins between the salt piers, and we have close to the salt piers. As we move close to the salt piers, we have lower resolution, lower amplitudes, and lower signal to noise ratio. So as I mentioned, we perform this sensitivity analysis. So we have our original seismic attributes. And then first we apply Kuwara median filter. The good thing about Kuwara median filter is like it's a smooth the transition. You see, it blocks the seismic, the phases, and it's sharp the transition between phases, between seismic responses. And then we also increase we add but limited seismic noise to try to decrease the signal to noise ratio to the seismic amplitude and then recompute the seismic attributes. So here I show you an example with coherence. We have the original case. Then with Kuwara, it looks smoother, better transition in some areas between more chaotic and less chaotic areas. And then in coherence, you see that we are starting having less differentiation between the response. And it makes sense. Like chaotic areas are way more chaotic now. And areas that were high signal to noise ratio, now we have some sort of random noise that is being captured by the attributes. So what we did is like we have this sensitivity analysis and we have 9 candidate seismic attributes. We have coherence, total energy, GLCN entropy and contrast. These are texture attributes. We have reflector convergence. We have spectral bandwidth, dip deviation, NA deviation, and convergence of dip. So these are non-parallelistic attributes and really, really good to quantify changes in dip and energy in between the reflectors. So these are the global interpretability. So in SHAP, you can, when you sum the results from several SHAP values from different data points, you can have like a general overview, your global response of the attributes. So we have the 3 cases, the original, the Kuwara, and the signal to noise ratio equal to 2, adding noise. We see first that for all these cases, the total energy and the deviation are the most important attributes, but then the attribute important changes based on the quality of the inputs. For example, with original attributes, we have total energy, deviation, and the energy deviation is the most important attribute, then coherence, and continue like that. Then with Kuwara filtering, we have still total energy and deviation, but now the spectral bandwidth is the 3rd most important attribute, and it used to be the 7th most important attribute in the original case. And when we have noise, total energy and deviation are still there, but now GLC and contrast is the most important. So you see that the attributes important is changing. Also, what we did with SHAP is we can analyze something called the SHAP dependence plot. So we analyzed 81 different plots because we have 9 attributes, 3 phases, and 3 cases. So with this, we can create like the set of rules that the machine learning model learns to perform the classification. So in a general overview, you have a particular voxel, and you say, okay, if this voxel is larger, if the total energy in this voxel is larger than 400, you might have NTDs on conformal sediments. If it's lower than 400, you might have, okay, salt or conformal sediments. Now, if you have the same voxel, but you analyze the deviation, if it's larger than 2, you might have NTDs or salt. But if it's lower than 2, then you have conformal sediments. If you have the same voxel, but now with a 3rd attribute included, GLC and contrast, if it's larger than 80, you might have salt and conformal sediments. But if it's lower than 80, you might have NTDs or conformal sediments. So what we saw here with all these rules is like using multiple attributes as input for machine learning analysis is a good approach when we want to perform seismic facies analysis, because maybe using some attributes, you might have several similar response between the facies, but in other areas, in other attributes, this response, you have larger differentiation. You have a larger difference between the seismic facies. So when you use all that information together, you have a better differentiation between the attributes, between the facies, sorry. So then we perform the seismic facies classification in the whole volume. We have the original case, we have the Kuwara, and we have the signal to noise ratio equal to 2, adding signal to noise ratio. And we see that Kuwara offers the best results. In general, for the 2 salt appears and the main mass transport deposit and conformal sediments, they give similar response. But then when there are some areas close to the salt appears that you see that you have some misclassifications in the original and the signal to noise ratio and the lower signal to noise ratio cases. In Kuwara, you have a better response. You have less misclassification. So what we found here is like is good to have some sort of precondition into your initial inputs to trying to improve the quality of the inputs as much as possible to have a better facies classification. Then when we use SHAP, okay, we have the global interpretation, but now in SHAP, you have your facies volume and you can go to this particular data point. So here I'm going to point A, and you see that the point A is a point in that was misclassified as mass transport deposit inside a huge salt appear. So we want to understand how that might be happening. So this voxel was classified with a 45% probability of having mass transport deposits. So applying SHAP, we have the result for these facies. So for the MTD facies, you see that we started with 33% because we have same probabilities, starting probabilities for each facies, final probability of 45%. The red attributes are increasing the probability. So you see that because we have a coherence of 0.7, spectral bandwidth of approximately 57 hertz, at the deviation close to 7, and a total energy of 700, all these attributes are pushing the probability up, increasing the probability. And then GLC and entropy of 0.52, and then covariance deep energy of 0.77 are decreasing the probability. So when you put all these attributes together and they work together, let's say in the machine learning algorithm, you have this final result of 45%. So now we can understand how these attributes are being used and try to put some explanation to this final output in the facies analysis. Another cool thing that we did with SHAP and is we can actually see how the machine learning sees the data. We can analyze that. So for example, if we have the original seismic amplitude and we can render the SHAP values in that area, so we can see that for the total energy of NTDs, red values are increasing the probability and blue values are decreasing the probability. So when you use total energy, you see that some areas that are correctly classified as NTD, so it's correctly classified, but you have some overlap with the conformal sediments. But you have a clear differentiation with the salt. If you analyze the total energy for the salt, you see that the salt using total energy is classifying really well the salt appears. Small misclassification with some areas like close to the seismic survey, but in general, it's classifying really well the salt appears. And when you have total energy with conformal sediments, you have good differentiation with salt, but really high overlap between the MTDs and the conformal sediments. Now, if you use deep deviation, you see that with deep deviation, you have really good contrast between the conformal sediments and the mass transport deposit. Slight overlap with the salt appears, but it's not that bad. With the deep deviation for the salt for that particular facies, it's differentiated really well. The salt appears. The edges are not influencing that much the classification because the values are close to 0. And you have a good differentiation with your conformal sediments. And finally, if you analyze that attribute for conformal sediments with the SHAP value, you have a clear differentiation between the conformal sediments and the salt appears and the mass transport deposit. So now with this SHAP, correndering SHAP with the seismic amplitude, we can try to analyze how the machine learning is seeing the geology in this case, seeing in quotes, So some preliminary observation of using SHAP for seismic facies analysis is first, the attribute important is dynamic and changes based on the quality of the input data and the seismic facies analyzed. So you saw that, for example, for NTDs, some of the attributes were more important than for salt and vice versa. So depending on the target seismic facies, you might have a different, an attribute that might be more important than other. So when we have a combination of attributes that measure changes in energy and deep, we are having better results to differentiate between mass transport deposits, salt, and conformal sediments. And finally, we perform this in-context interpretation, try to analyze how the seismic reflectors impact the classification by correlating SHAP with the original seismic volume. We see that there are some overlap between mass transport deposits, salt, and conformal sediment, depending on which attribute you might be using. So with this knowledge, we might now refine the model and say, okay, I will use these attributes because I have a better differentiation than using this one. So now we have a better understanding what's happening inside the machine learning algorithm, and we can go and refine and update the model if necessary. So now, Heather, thank you.
Yes. So I'm just going to spend like 3 slides showing you a non-seismic application of, no, go, yeah.
Yeah, I don't know what happened.
Okay, a non-seismic application of SHAP, kind of explaining it my way. So as a little bit of a backstory, I do some work at OU with social scientists. And during one conversation with them, I was kind of thinking like, oh my gosh, just give me some rocks, because I understand rocks better than I understand people. Like, their brain is a black box to me. So that immediately made me think of machine learning and trying to use explainable AI, in particular SHAP, on human data. And so in this case, what I did is I used a social survey that a group at OU had collected a few years back on Oklahomans, trying to, just understand a lot of different factors, from severe weather to earthquake experiences. And I was interested by the earthquake experiences and induced seismicity, thinking of it in terms of what happens for carbon capture, geothermal, or wastewater injection if we have induced seismicity. So the way I thought about SHAP, and the way I explain it here with people, is that we have our human on the left, and they've got their black box of a brain, and I've got a question mark because I don't understand what's going on. But from that survey, I have an idea of what that individual's opinion is on the seismic risk, on earthquake risk. And I know from the survey things, many factors, some of them being their political party, or their ideology, their experience, and like how they perceive extreme temperatures changing, or hurricanes. We don't get our hurricanes in Oklahoma very often, but tornado risk, hail, those types of things, their education, and other like socio-demographic factors. And then I can use SHAP to look at the same thing that David was showing with looking at one pixel. I can look at that person's SHAP result and how that kind of contributes or doesn't contribute to their perception of earthquake risk, the risk of induced seismicity. And so, like in this case, for this person, I'm showing red. They're liberal. It's red. It's positive. It moves them towards having a higher perceived threat of earthquakes. So does being a Democrat. They haven't noticed any extreme temps, so that kind of lowers their perception on seismic risk. So it's kind of working in the same way. So if you go on to the next slide. So what I could do is I could do that local type of SHAP result like I showed in the last slide, or I could do a global one where I look at, all the people in Oklahoma who responded to the survey. It was like 2,000 or so people. And one of the things I noticed was that the most important feature, and I'm plotting these a little bit different than David did, was if they had experienced an earthquake. And so I could also compare their zip code to the Oklahoma Geological Survey earthquake catalog and get an idea of if they were likely to have actually experienced an earthquake, or they think that they're just happening more often. So I could do a lot of background work like that. And so one of the things that we noticed in the survey is that people Oklahomans who experienced an earthquake are more worried that they're going to continue to happen in the future. And so that kind of ties in with the psychological theory called construal level theory, which means that when events happen to you, suddenly they seem more present. Like, they're not this abstract idea of having an earthquake that was caused by induced seismicity. All right, next slide. And so we could also look at these interaction charts and try to understand if two of the variables are playing together. And David's done this also in the seismic attribute work too. It can be done with all the different types of data. But what we notice is that there's a very strong interaction of believing that there will be more seismicity and over predicting seismicity to continue to happen if they've experienced an earthquake and if their age overall. So if you go to the next slide, we can look at these interactions, and you could, thanks. And so you could plot them side by side. And so the same thing can be done with the seismic attribute data. And we can look at the patterns of how things change through time. So there's not always like a linear effect between age and experiencing earthquakes, but rather we note that in this case, some of the younger folks overestimated past seismicity, and so did some of the older folks, so on each end. We also noticed when we put weather in an extreme, like all different types of extreme weather, that people who experienced more extreme weather, they also tended to overpredict seismicity. So that's, just a quick look at the many different ways you can use SHAP to explore what's going on in random forests and other types. So I just wanted to conclude, or we wanted to conclude with a quick slide just saying that these explainable AI methods, of which SHAP is just one of them that we're studying up at OU, they can be really invaluable for understanding what's going on in the machine learning inputs. And so I think of this, I think back to my early years at Chevron drilling wells and whipping out a coherence map, trying to show where the faults might be, how close they are to the wells I was proposing. You know, if we start using machine learning, sometimes we have to explain to other people what exactly is the machine doing? Like, we don't want to base these $1 million decisions to drill a well or whatever on this black box algorithm. And so SHAP can help us kind of peer into the results a little bit more to give us more confidence that we understand what it's doing, you know, logically. And so one of the things we both mentioned is that SHAP in particular, it can provide insight at a very global scale. So overall, what's going on with those MTDs, or at a local scale. So why is that one pixel being misclassified? And like I mentioned, SHAP's just one of them, one of the exploratory methods that we've been using up at like our AASPI consortium. So LIME's one that David and I are working on for image, and some of my other grad students have been working on it in PCA. And so we'll just end by, of course, acknowledging the seismic data we got from PGS, the earthquake data and the survey from the Center for Risk and Crisis Management up at OU. And then all of this is sponsored, and this research is sponsored by the different companies that sponsor our consortium. And so if any of you happen to work at these companies, you have access to the SHAP. And you could just shoot me an email and I'll let you know how to download it, because we have SHAP already in our AASPI software. And if, you know, I'm always happy to chat with anybody else who's interested. But thank you for all your time, and we could take questions.
Any questions? There is one question in the chat.
Okay.
2 questions now.
All right, let's see. Colin asked, is it possible for machine learning to go directly from seismic to the MTD salt conformable sediments? No, we haven't done that before. We usually calculate all the attributes and then decide which attributes would best work in the algorithm and then put it in. Do you know how to do that?
No, that approach.
Could I comment on that?
Yeah, go ahead.
Approach, like,
go ahead, sorry. You know, it seems to me that all the information needed to compute the attributes exists in the seismic, right? The attributes just come from the seismic. So it would be possible, I would think, to use either supervised or unsupervised classification to do the same thing. So supervised would be where you get an experienced interpreter to point out where there's MTD or salt or conformal sediments. So giving examples to machine learning and let it rip and do the classification itself, or even unclassified, where the machine learning just distinguishes 3 different, you just give it, I want to have 3 classes. So it's not clear to me why you would need to compute attributes, because all the information to compute attributes is in the seismic itself.
So,
sorry.
You go, David.
Go ahead. Okay.
I was gonna say, so we've asked ourselves this question because you can just automatically calculate out attributes. You could say, here's 50 attributes, figure out what's best. And I challenged one of my students a few years ago, Crelia Lamarca, who recently got her PhD, and one of her projects was trying to pick attributes to put into the algorithm based on like geologic interpreters' knowledge, or just picking them out mathematically like an algorithm would do. And we actually found out, at least in the case for channels and channel facies, that the human, with their little bit, extra interpreter knowledge of picking out the best attributes, did a better job of getting better machine learning classification. So you could do it without any human in the middle and just calculate the attributes, tell it to pick out which, 10 are the most different with like a PCA or ICA analysis, but it may not be as optimized.
Yeah, it's not clear to me you need attributes at all if you have the seismic data.
Yeah, what you're proposing is an end-to-end deep learning approach. I haven't seen the results, right? I have seen results, people trying to do that with fault classification. I think with fault classification works really well because you tend to have low discontinuous, low amplitude. You can pick that fault really well. I don't know what will happen when you have the salt mass transport deposit. Just thinking like mass transport deposit in this case, you have this combination between high amplitude, low amplitude reflectors. I would like to see how just an end-to-end deep learning approach works in that area because the low amplitude part of the more chaotic might match a little bit with the salt. The high amplitude might match a little bit more with conformal sediments. I'm just curious what will happen. I haven't seen any case of that. The other thing with the end-to-end deep learning approach is data, how much of data you will need. So with this, we just train this neural network with this random forest with 10,000 samples. That's it. It's a small number of samples. It's performing really well. First classification accuracy was 92% probability, and 92% accuracy, sorry. So in that case, I would like to see that application. To be honest, we would be curious to see. I would say that for a complete end-to-end deep learning approach, trying to differentiate between these three phases, you might need a lot of data, and that will, yeah, you interpreter will need to go and pick maybe the whole line, try to do maybe a UNet to try to segment between the original volume and the classified volume. You have several inlines. I don't know. It will be curious. I think it will be a lot of time consuming. With the attributes. You can go ahead, compute the attributes really fast. We have that technique well established. We know what is happening with the attributes really well. And then with the big polygons, yeah, we have to pick polygons. This is a supervised approach, but it's just like we have to pick just a few polygons to try to differentiate between the faces. We didn't have to approximate the whole inline. Another thing that we didn't mention here is like what happens when you have artifacts. For example, what happened in one of these classifications, and I suspect that that might happen to the end-to-end deep learning approach. It's like multiples. In multiples, they were misclassified as MTDs or conformal sediments. So because we didn't train the machine for multiples. So in that case, it's like if you do the end-to-end deep learning approach, you might need to segment the whole volume to say, okay, this is all, this is entities, they're conformal sediments, but then you have to go in all the details. This is multiples. This is another kind of noise. This is just edges in the seismic. So I don't know. It's curious. It's a good approach. I would like to see what happens if someone tries with this particular target, with these three phases. Thank you. Yeah, so we have another one here. Let me see, it's possible to correctly, okay.
Jim is gonna say something.
I was just gonna
Yes.
respond to Colin's question because it kind of I was asking the same thing to myself, and I realized humans, we have a poor job of asking the right question to start with. And we always get the answer to the question we ask. And that's our problem. So now we go to a computer and there's so many degrees of freedom when we ask them to find the most three obvious classifications. We're not really asking the three obvious classifications. We're actually asking for some biased output from that data. And there's so many degrees of freedom. So what you're doing, I think with this data attributes are you're trying to find reducing those degrees of freedom like continuity or spatial extent. And these attributes then allow us as humans to better point out, I think, what the question we're trying to ask. And again, it's a way of training the data sets. Have always been concerned that you put in bias, but in reality, the seismic is so underdetermined, it's really hard not to actually have to provide some control, whether we know it or not. Just because if Colin was right, we could just take the data off the back of the boat and give it to the computer and say, tell us where the salt is. I'd like to see us do that, but the data is so large and it would take so long to reduce. So imaging is one step that we do as part of that machine workflow. And I think attributes are just another example of that.
It's a good point, Jim. In here, when you compute the attributes, you're trying to put your knowledge as an interpreter, what might work, what doesn't work, to try to reduce the dimensions of freedom. Yeah, that's true. So, okay.
There is another question from Jake.
Yes. So with the correlations, that's a good question. With the correlation, that's that's not, it's not simple to answer, because I know a lot of people that talk like you cannot use high correlated attributes because it might not don't work. But I think the key point here, the word is redundant attributes. I did some research before this one in my PhD that I tried to analyze more about this correlation and redundancy of the attributes. And what happened is, like, if you have actual redundant attributes, like the correlation is close to 100%, and it depends how you're measuring the correlation. I was using Pearson correlation in general, but there are several ways to measure it. So when you have redundant attributes that is close to 100, like they actually provide basically the same information, yeah, you can discard one of the others, you know, like, and you will see that when you try to do some sort of attribute selection, when you put those attributes together, the performance tend to decrease, definitely. But one thing that I also noticed, and some other people in that area of the research, is like when you have highly correlated attributes, but not redundant, like maybe 80% Pearson's correlation, 75% correlation, they tend to help to each other. You know, they try to, that's the way that I describe it, tend to help to each other. So I compare what happens if you don't use them together and what happens if you use them together, and you have to have better definition, better facies classification in this case. So I would say that in this particular approach, the target wasn't more about the correlation between the attributes. In my experience, I don't like to use Pearson's correlation to try to say, okay, I'm not going to use these attributes because they have high correlation. They might help each other, as I said. I would like actually to use, well, first, if they are not redundant, that's perfectly fine. And then after that, I would like to evaluate the performance of the model itself. What happens if I use these different combination of attributes? Is increasing, is decreasing, and then evaluate the model itself, the results of the model. But in this case, we didn't focus in the attribute correlation part. We actually did this sensitivity analysis, like saying 9 attributes, saying hyperparameters for the model. The only thing the model is changing is just the inputs and the quality of the input in this case. And that was the main target here. One thing that I must suspect, if you have like really high correlated attributes, or might have like redundant attributes, like probably their SHAP values are gonna be close to 0.
Yes,
I think that's
and
my main assumption, that they are gonna be very low in the list. But as I said, that wasn't the main focus in this research.
Yeah.
So
No,
thank
I've
you for the
seen that
question.
in some other things, David, where SHAP will, if you have two that are very similar, one of them will get dropped all the way down. So that's one way that you can notice it also. But we have noticed, I mean, it's kind of a side project, but in terms of using similar attributes, is one of our students who is just finishing up a master's project. He's trying to do classification on 4D data. So he's using the same attribute, but on the base and the monitor. And that's been really revealing, because, you know, that slight difference that would be the fluid change through time, that's being picked up by the clustering technique that he's using. So sometimes just subtle differences between two attributes can be quite helpful, depending on the question you're asking.
So another question that we have here is, what is the percentage of data you use to train your model? So we're using an 80 to 20% split ratio. I don't remember the exact numbers and the paper, but it's like around, I think it's around 10,000 samples for training, 20% like from the total. I don't remember, like maybe 3,000 samples for validation, something around that. But I would say like around 15,000 in total samples. And if you compare that to millions of samples in seismic, it's like really low percentage of samples that we pick in the seismic, you know. So I don't remember the exact numbers, they are in the paper, but it's a low number of samples compared to the whole volume. So yeah. And then how were the seismic data processed in your Gulf of Mexico examples? I don't know exactly. Like I didn't have access to the processing report, to be honest. So I don't know any of the details of how the seismic data was processed. That was data that Dr. Kormarfu had here for research and education. So I use it, but unfortunately I don't have I don't have the processing report, so I don't know the details. Yeah.
Any other questions? I do have a question regarding how do we limit, you know, all the possible solutions that you're getting with this approach. And I'm thinking about when we do like model building, and I know I'm going back to model building and data processing, but you're relying on the data that has been processed, and of course there is a lot of uncertainty when you do that, but sometimes we can use additional data such as well data, gravity, and MAC. Is there a way to implement or add more data to it that is not in the seismic domain, but in a different domain? Or this is something that the interpreter has to use and then pick horizons and guide the algorithm somehow?
So for now, it's something that the interpreter does outside,
Okay.
like using the well logs to help, know that, okay, well, this classification for whatever method is sand, shale, salt, that type of information. I am recruiting like 4 or 5 new students for the fall, and one of our focuses of this incoming graduate student group with AASPI is to try to do more well to seismic work in terms of correlation and machine learning. So that's a focus moving forward over the next couple of years for research, because it would be really, really great to figure out ways to combine different types of data more seamlessly.
Mm-hmm. Okay.
Yeah, well, I've seen some research, some random forests to try to in the seismic data. They was part of the co-author. So the main target was like try to define the facies in the well data. The data was extracted in the well data, was trained with the random forest, was trained with well data, and then it was using pre-stack inversion. So we have the P impedance, S impedance, we have density, but I think it was just P impedance and S impedance at the end. And then we just use the model trained with the well data, the data extracted along the well data and apply that model to the whole volume. I have a final result with the facies that we define using well data, and then we just look for areas that are more the target for possible CO2 sequestration. So I have seen some cases. I haven't seen any case to integrate SHAP in particular with both, like with well data and seismic together. I have seen some applications with well data, and then this application with seismic earthquake risk information, but I haven't seen any integration. So that will be fun research topic for sure.
I want to ask one obtuse question if
Sure.
you still have time.
Yeah.
All right. I always try to think of these things as signal processing. Maybe that's my background, right? And I think of AI in this approach, you're solving simultaneous equations, essentially. It's a different engine for solving an overdetermined problem, hopefully. We have a lot of underdetermined problems as well that we try to do with AI. But there's kind of 2 concepts. I was wondering if the SHAP has more than one objective kind of output that it could get. There's 2 things. One, you could get the total signal. You get that, the salt body, but it's encased in noise. But that's what you really want. You want to know where it is, absolutely give me anything that is in the salt. All right. The other one would be give me the best picture of the salt. All right. Which is a different answer. You might have to throw out pieces of the salt that are noisy because you don't want to, by giving you just a pure signal, you can interpolate with your eyes or your other information. So is there something like that with SHAP that you say, give me the best correct answer or give me the highest signal to noise answer? Is there some sort of way to?
No. So the way that works is like you have your inputs, you train it somehow to have your targets, and you have your results. In this case, either a seismic classification, for example, or the risk assessment. Earthquake risk assessment, but then with SHAP is try just completely Shapley values to try to put weight and importance to the inputs. So I'm just trying to explain the final probability based on the inputs. And then what SHAP is doing is just approximating a linear model. So this linear model is like weights multiplied by the attributes, and when you sum that plus the base value, give you the final probability. That's basically the main idea of SHAP. There is no like give me this or give me that. I would say that selection will be in how you train your model.
Gotcha.
So depending on how you train your model,
I could train it so I want to see the geometry of the salt, or I could train it that I want to get the best estimate of the property of the salt. I guess that would be 2 things I could train for. I guess.
Yes,
Got
like
it.
one thing with the geometry will be like this. The thing with random forests and some other techniques is like these are voxel based. So how do you define geometry when you go voxel based? That's more difficult. You know, it's just like one voxel classify, one voxel classify. I would say like when you have geometry, what might relate more with Collins and response, like maybe you need some sort of UNet or something that actually sees a window to try to see the pattern. But as I said, it's like how you compute what is you looking is how to the way of different of seeing this. Like if you see the salt as a whole, okay, this is the shape of the salt. But if you see the salt as a tiny pieces, like how is the SHAP the salt response in particular, like high amplitude, low amplitude, chaotic, not chaotic. So it's depending on how the big picture or the small picture, how you want to approach the problem. Yeah.
Gotcha. But it is a good challenge for you all to go beyond inversion, which is like a single trace, and do what the FWI people are. They're doing whole wave field images, and that's really powerful what their inversions are, because they're not a trace by trace inversion, right? So you can imagine that you've got these geometrical properties that have taken some sort of window, right? And you can make that window as large as you want in geometrical attributes. There's no reason you couldn't do that also in your voxel attributes as well. There could be prediction error functions that you could have, or something else to say I put in a box of pixels rather than a single seismic sample.
What I've been trying to do lately is well, you can put the window part in how you compute the attributes. Like for example, if you have noisy data, you might use a larger window to try to compensate because it's high noise. If you have a really high resolution data with low noise, you might try to have like smaller windows. So you might change how the window, how to see the response at the attribute level in that part in the attribute computation. One thing that we are trying to think in this case is like how we can incorporate probability. So we are doing some sort of research, like this is completely different, but it's a UNet that to predict faults. But then how we can incorporate, because when you pick, it's like listed faults, and when you pick faults, you might have high amplitude, but then there are some parts like you can actually not see the fault. It's just your interpretation. Like I would say like the fault continues here, but you have less confidence, let's say. We are looking for ways how we can incorporate the confidence in our picking when we pick what is a fault and what is not a fault as part of the machine learning, you know? So it's not just my label, like 1 or 0, it's like how probability. I'm more confident or less confident, how to put that as a part of the machine to have maybe better results. We are still thinking some ideas, it's some work in progress, but that might be also something to take into account, how you can incorporate your confidence in your interpretation when you're picking the labels for machine learning.
Well, David, that was a really good example, because we did have a SEG Evolved China team that tried to run a fault picker on Gulf of Mexico data on the shelf, and it did okay shallow, but all of a sudden the listed faults kind of show their head, and it totally got lost, and it was almost an embarrassment, and it kind of begged the question, well, why couldn't it have a more complicated model to understand? Because if you looked at relative dip, it would have showed you had all these sort of events that would have lined up in the listed fault plane. So yeah, it's interesting when you pose that question of the training set and how the training set may have to vary spatially. That's getting a lot of challenge to but that's your challenge. That's the next generation, right?
The key point with fault is like, what is the fault response? Like sometimes you have clear discontinuities, and that is a fault. What happens if you have really small vertical displacement? Like you might infer as interpreter there is a fault, but for the machine, there is no discontinuity. If you train it looking for discontinuities, it won't be able to capture that unless you train it some differently. I would say that with the electric fault, that's what happened. You have less, like the image is not that well, it's more an interpretation. You will maybe it's going through here, but when you go to the data itself, definitely that attribute response there, the seismic response of that fault at that level is way different than the upper part that is more vertical displacement and sharper and look nicer. So yeah, that's how us as an interpreter go and try to do that interpretation, right? So
yeah, I think we've been trying to solve that problem through at least 2 rounds of grad student
yeah
so far. It's been a topic that we're been thinking about for years.
Any other questions before we end the meeting today? Well, I guess that's it. So thank you, Heather. Thank you, David. This was really good. Thank you. I know that you're taking your time off to do this, and so we're very grateful and very honored to have you today speak to our community.
Wish we could be there in person.
Yeah, next time. So for sure.
Okay.
So if you guys are coming for emails, we can coordinate and see.
Okay.
Great. Thank you very much for the invitation. Thank you very much for all the questions.
Thank you so much.
Thank you.
And for the one, somebody was asking about the recording. You can access the recording on the website. So if you don't know how to access it, you can email me or email Kathy or anyone from the society, and so we can give you access. Thank you. Thank you so much. Thank you. Bye.
Bye.
Bye.